Well, hi everyone. In this video, I'd like to discuss the annihilator method for solving an nth order linear differential equation. I'm going to assume that you've already studied the technique for solving a homogeneous nth order linear differential equation. And in this video, we're going to focus more on the non-homogeneous differential equation that we could write in the form L of y equals capital F. Remember that L is my derivative operator that should be of order n for this application. Y is the unknown function that we're trying to solve for. And in general, the right-hand side of our differential equation could have any function f of x. And in that case, we have a non-homogeneous differential equation. To solve this type of equation by using the so-called annihilator method, we're going to carry out a three-step process. So let me write down the three steps here, and then we'll discuss how this works. A three-step process. The first step is going to be to solve the associated homogeneous differential equation. So what we're going to do first is solve L of y equals 0. This would be the homogeneous differential equation, right? For what I'm going to call the complementary function, this is the word that is associated with the solution. And this would be denoted as y sub c of x. So this technique is something that we've already discussed earlier, that if we have a homogeneous differential equation, if it's nth order, if it's linear, and in particular, if it has constant coefficients, we certainly know how to write down a trial solution and obtain the general solution to that corresponding homogeneous differential equation. So this is the associated homogeneous differential equation for our general non-homogeneous differential equation, L of y equals F. So the first step is to solve the corresponding homogeneous differential equation. Now, the second step is going to be to find one particular solution. And we only need one. Just need to find one particular solution. I'm going to call it y sub p of x to the non-homogeneous differential equation L of y equals F. Okay, and so here you might want to mention that we can see below, because that is what we're mainly going to be talking about in this video, is how to do step 2. How do we find one particular solution to the non-homogeneous differential equation? And in many situations, we can use this so-called annihilator method. So I'll discuss that in just a moment, but let me finish writing down the third step of our process here first. And the third step is to write down the final answer, the general solution, and that is given by the following: y of x equals the complementary function y sub c of x plus the particular solution that we found in step 2, y sub p of x. So as you can see, step 3 doesn't have a whole lot of meat to it. All you really have to do is take the work that you did in steps 1 and 2 and add those results together to write down the final general solution. Sometimes, in fact, if the complementary function or the particular solution are particularly long and tedious to write out, then when we get to step 3, all we really need to do is make sure that we've identified the complementary function and the particular solution, and we can just simply write down what I've written here in this box as a final answer without recopying the complementary function and the particular solution again. Okay, so the main thing we need to discuss here is step 2. I'm going to assume that if you're watching this video, you've already learned how to do step 1, and obviously there's not much to step 3. So it's step 2 that we primarily need to be working on in this annihilator method discussion that we're going to have right now. The way that we're going to carry out step 2 is we're going to take our non-homogeneous differential equation, and the strategy for what we will do with this is we are going to try to find a so-called annihilator operator. So the strategy is to find an annihilator. And when I say an annihilator, I'm going to be talking about an operator. That operator involves derivatives. So it's a derivative operator. So we'll call it A of D. Capital D is my notation for the derivative operator. And we're going to try to find an annihilator operator for the function capital F. So in other words, what I'm saying is we're going to look for some way to take capital F and annihilate it using derivatives. Okay, that's actually what I really mean here, is that I'm hoping to figure out how to annihilate capital F by using derivatives. The idea behind this is that if I start with L of y equals F, and I apply this operator, this annihilator operator, to both sides of my given differential equation, what will happen is it will turn my differential equation back into a homogeneous one, right? Where we have a 0 on the right-hand side. If we have a homogeneous nth order linear differential equation, we already have discussed how to solve that. And so we would be able in that case to solve for a solution to this differential equation. This is kind of going to be the idea behind it. Before I get too deep into actually implementing this strategy, I just want to take a moment to talk about annihilators in general and how you can figure out an annihilator operator for something. And so just to give you a couple of examples, let's suppose that capital F of x was, I don't know, x squared, let's say. All right. And let's suppose we wanted to use derivatives to annihilate that. Feel free to pause the video for a moment if you want to think about it for yourself, how you could use derivatives to make the x squared become 0. If you think about it for a moment, you might realize that as you take derivatives of x squared, maybe more than once, you can actually eventually turn this into 0. And in fact, you can do it by actually taking 3 derivatives of x squared, which I'm going to denote with the operator d cubed. If I take 3 derivatives of x squared in succession with one another, I will ultimately end up with 0. So the annihilator operator for x squared would just be d cubed. More generally, for any value of k greater than or equal to 0, if f of x is just x to the k, so if f of x just consists of some power of x, then we can annihilate this by just taking one more derivative than whatever power of x we have started with, right? So if I have x to the 5th, I could annihilate it with d to the 6th. If I have x to the 9th, we could annihilate it with d to the 10th. Now, this is only really applicable for positive whole numbers for k. You could imagine that if k was a fraction, or if k was a negative number, then annihilating that function x to the k might not be a simple matter of just using d to the k plus 1 power. So this is really intended to be used for whole number non-negative integers. Okay, but that's a good start in terms of thinking about annihilators of functions. Let's take a slightly different kind of function. Let's suppose that f of x was something of the form e to the ax. This is a very common function, and maybe this is on the right-hand side of our given differential equation. The question is, how could we annihilate it by using annihilators, derivative operators? Well, if you start taking derivatives of e to the ax, as you know, the only thing that happens is factors of a get pulled down in front. And so you'll have a or a squared or a cubed, depending on how many derivatives you take. You're never going to literally just obtain 0 by doing that. But what you can do is you can recognize that one derivative of this function would give you a times e to the ax. And if I then subtract a times e to the ax, I would actually get 0. So what I'm going to try to have you think about for a minute is that we could have an annihilator that looks like this, d minus a, right? If we just check that out, if you're not quite convinced, just try it. Apply d minus a to e to the ax, and take a look at what you end up getting. Well, you end up getting the derivative of e to the ax, which is a e to the ax, minus a times e to the ax, and sure enough, that has been annihilated to 0. All right, so this is for any value of little a, the annihilator of e to the ax is simply d minus a. Pretty nice. That's a pretty easy one to implement as well. Let's try another one. What if we took f of x to be, let's say, the cosine of bx, or in fact, we could even, at the same time, we could think about the sine of bx. And I want to annihilate the cosine or the sine by using derivatives. Well, if we think about that for a minute, you may remember from calculus, when you take derivatives of sines and cosines, they kind of flip back and forth. But if I were to take two derivatives of either one of these functions, I would end up back with the same kind of function again. So two derivatives of the sine function is just the sine function again. And two derivatives of the cosine function is just the cosine function again, except that there will have been a sign change. Plus minus change, right? So if you take two derivatives of cosine, you'll be back to negative cosine. If you take two derivatives of sine, you'll be back to negative sine. And in the meantime, using the chain rule, you would have been pulling factors of b out in front. So I actually claim that for either one of these types of functions, the annihilator would simply be d squared plus b squared. Okay, d squared plus b squared. Let's just check it out with one of them. Let's take d squared plus b squared and apply it to the cosine of bx. All right, so if I were to take two derivatives of cosine of bx here, right? Let's see, the first derivative would be negative b times the sine of bx. And when I differentiate that again, I would get negative b squared times the cosine of bx, right? And to that, I have to add the second term, which is the b squared times the cosine of bx. And look at that, it completely cancels out to 0 again. So the annihilator of either cosine of bx or sine of bx is just d squared plus b squared. Okay. Another thing to take note of here, guys, is that if you had constants in front of any of these functions that I've used as examples here so far, it would not change the annihilator of those functions. So if I wanted to annihilate 8x squared instead of x squared, I can still do it with d cubed. Or if I wanted to annihilate 5 times the sine of bx, I could still do it with d squared plus b squared. Putting constants in front of any one of these has no effect on what the annihilator would need to be. Moreover, I will give you one more additional remark here, which is very important, which is that if your f of x happens to be, let's say, a sum or a difference of other functions. Let's say we had f1 of x plus or minus f2 of x plus or minus and dot, 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 right? And imagine that you wanted to annihilate something like this. So this could be, you know, e to the 3x minus the sine of 5x, right? Plus x to the 10th, something like that. If you had additions and subtractions of some of these kinds of functions, then it turns out we can annihilate those as well with a simple procedure, the annihilator of a function that is built up as a sum or a difference of a bunch of other functions is obtained by actually multiplying the individual annihilators. So you end up multiplying them. Please be careful about that. Additions and subtractions have to be turned into multiplications when we move to the realm of annihilators. So I'll leave that as a detail. I'm not going to verify exactly how that works right now. It's not too hard to show this though. And so that allows us to sort of annihilate linear combinations of powers of x, exponentials, and sines and cosines. Okay? And that's a pretty good start. That's a pretty good start. We also can combine these functions under multiplication as well. So I could take a power of x times an exponential function times a sine or a cosine. And it turns out that there's an annihilator for those as well, not nearly as quick to verify. But what I have done, for those of you who have access to my Canvas homepage, I'm going to show you right now that you can actually find in the Canvas page a copy of some of these annihilators. So if we look at the special handouts folder in Canvas, there is a document here that's called Annihilators and Integrals Table. And if we open that up, what you're going to see on this table is a list here at the top of a number of these annihilators that I've just been talking about. And so this would be a handy document to keep close by, because if you're solving a non-homogeneous nth order linear differential equation where the f of x is any kind of linear combination of any of the 9 forms that are listed in this table right here, then you can just use the annihilators that are provided here to help you to do those problems, because we're going to need to be able to find annihilators for these functions. So again, just wanted to point this out. You can find this table in Canvas in the special handouts folder. Okay, great. All right, guys, I want to put this all to a big test right now. And I want to take a function f of x that's pretty involved and see if we can just write down the annihilator for it. In order to do that, of course, we're going to use the annihilator table that I just shared with you. The idea here is that f of x is a combination of several terms. And so I'll remind you again that we can just figure out the annihilator of each individual term and then multiply the results together. Okay, that's how we're going to approach this. So the first term here, which is 8 times x to the 5th, I'm going to call the annihilator of this one a1 of d. And keep in mind that the factor of 8 in front has no effect whatsoever on the annihilator for that term. So I just need to think about the annihilator of x to the 5th. And I can either do that one kind of in my head, or I can refer to my table of annihilators that I was just sharing with you a moment ago to write it down. It turns out this one is just d to the 6th. 6 derivatives will annihilate 8x to the 5th. Okay, what about the next term? Notice there's a minus sign here. If it's a plus or a minus, doesn't matter. But we can now calculate the second annihilator. I'll call this a2 of d that corresponds to this term. So if I look on my table of annihilators that I just shared with you, this would be covered by item number 6 in the list. The factor of 3 makes no difference. We can ignore that, but we need to focus on e to the 2x and the cosine of 5x part of this. And the annihilator is d squared minus 2ad. Now the a here is 2. This is the little a value of 2. So 2ad would be 4d, and then plus a squared plus b squared. That would be 2 squared plus 5 squared. 2 squared plus 5 squared is 29, right? And so that would be your annihilator for that second term. Again, I'm getting this off of the table of annihilators. This is not one that you would necessarily memorize ahead of time. Okay, what about the next term? The third term here has a factor of 2 in front of it, which we're just going to ignore. And I'm going to focus for the A3 of D, the third annihilator, on the rest of what I see here. I have a factor of x raised to the first power. In my table, that's going to correspond to k equals 1. And then I have e to the 3x times the sine of x. So I have an a value of 3 and a b value of 1, again, in connection with the forms that are listed in the table of annihilators. So what we're going to get out of this term, my friends, is we're simply going to have d squared minus 2 times the a value of 3, that becomes a 6d, and then plus a squared plus b squared, 3 squared plus 1 squared is 10. All right, and this time, because the k value was 1, you'll notice in our table of annihilators that we have to add 1 to that for an exponent. So this will be a squared exponent. By the way, this one is item number 9 in the table of annihilators. Okay, definitely helpful to have that table in front of you. If you don't have it in front of you yet, I would recommend pulling that up while we're having this conversation, because it's really helpful as we go along. I'm not expecting anybody to have these memorized. Okay, and then finally, the last term here, I'm going to create a fourth annihilator for this final term, which is 4x squared e to the 7x. The factor of 4 does not matter at all, of course. And here I have x squared, so the k value is 2. And e to the 7x, e to the 7x would normally be annihilated by d minus 7. But I'm going to power that up to the third power, because again, the formula, in this case, it's item number 3 in the table. We have to put an exponent on this that is 1 more than the k value on the x to the k. Right, so I have calculated all of the annihilators of all 4 terms. And so now the annihilator, the overall annihilator of my entire function f of x is just the product of each of these 4 individual annihilators. This is how this works, okay? So what we'll have is d to the 6th times the quantity d squared minus 4d plus 29 times d squared minus 6d plus 10 quantity squared, right? And then times d minus 7 cubed. That is it. That is the annihilator of this function capital F of x. All right, so the first task in understanding how the annihilator method works in our study of differential equations is to be able to actually compute them, to compute annihilators for things that are in this table of annihilators right here. That would consist of powers of x, integer positive powers of x, I should clarify that, as well as exponential functions, as well as sines and cosines. I realize there's lots of other functions out there in the universe, but at least for this time being, we're going to focus just on functions that are combinations of powers of x, exponential functions, and sines and cosines. Okay, with that in mind, now I think I'm ready to discuss how we use annihilators to solve differential equations. So for the rest of this video, I'm mostly going to be trying to solve some differential equations by using the annihilator method. In fact, the best way to sort of learn and understand the annihilator method is to just take on some examples. So the first one I'd like to do is a relatively easy one. It's right here on the board behind me. Solve y double prime minus y equals 16 times e to the 3x. I'd like to show you how to solve this. We're, of course, going to use the 3-step process over here. So to get started on that, it might be helpful to rewrite the equation in the D notation. So the left-hand side is really just two derivatives of y minus y, which we can express as d squared minus 1 of y equals 16e to the 3x. Okay, and in order to start step 1, what we know is that we need to solve the associated homogeneous differential equation first. Well, that would be the following. So the homogeneous differential equation, we essentially are just going to ignore the 16e to the 3x. So we're going to have d squared minus 1 of y equals 0. So we make the right-hand side equal to 0 for this. And we've learned in the past how to solve a differential equation like that. We have to start by writing down the auxiliary equation. And that's obtained by just changing all of the d's to r's. So in this case, we would just have r squared minus 1 equals 0. And we immediately obtain the roots plus or minus 1. Notice that we have no complex roots here. We also don't have any repeated roots here. These are just two distinct real roots. So it's very easy to write down the general solution to this homogeneous differential equation. I'm now going to call this y sub c of x. That's the complementary function in the new lingo we have for this. So y sub c of x is going to be c1 times e to the x plus c2 times e to the negative x. So this part should just be review. This is just review of earlier material when we were looking at homogeneous nth order linear differential equations. So now I want to move on to step 2. This is where the new stuff comes in. And the first thing you're going to want to do on step 2 is identify an annihilator for the function on the right-hand side. In this case, I have 16e to the 3x. The 16 doesn't matter, it's just a constant. So I'm mainly focused on annihilating e to the 3x. And we can either simply remember what that annihilator is, or we can consult our table of annihilators. In this case, the annihilator is just d minus 3. Now, what I had suggested earlier is that we could apply this annihilator on both sides of our differential equation, right? So we go back, I'm going to go back to the d notation of my original differential equation, and I'm just going to apply this annihilator on both sides. So you'll have d minus 3 being applied to d squared minus 1 of y on the left, and on the right, d minus 3 is also being applied to 16e to the 3x. So you simply apply that annihilator on both sides. The reason for this is, of course, on the right-hand side, when you use the annihilator on the function, you annihilate the function. It's going to become 0 on that side, which means that you now find yourself with another homogeneous differential equation. And so we know how to solve this one again, right? The auxiliary equation this time would be r minus 3 times r squared minus 1 equals 0, right? So in this case, my derivative operator on the left side consists of both of these factors, okay? Now, this auxiliary equation has roots that we can see, 3 and plus and minus 1. But what I want you to make sure you realize here is that whatever the old roots were, I'm going to call these the old roots, the roots that we obtained in step 1, we're still going to find them coming along in step 2 as well, right? Because we still have this d squared minus 1 here. What we've done is tacked on another new root. So the r equals 3 is a new root to our auxiliary equation that we have over here, but we also will have the old roots as well. This is not just an isolated occurrence. This will happen on all of these problems. We will have the old roots that we already saw in step one with some new root or roots tacked on. Those new roots are coming really from this annihilator that we had calculated. So the new root is coming from the annihilator. So let me just emphasize that this comes from the annihilator of capital F of X, A of D, right? And the old roots, those already got used in step one when we calculated the complementary function. So what this is going to suggest is that the old roots are reserved for creating the complementary function, the solution in step one to the associated homogeneous differential equation, while the new roots are associated with step two, which is where we're going to write down the particular solution. And those new roots are associated with whatever the annihilator was. So I'm trying to sort of cut the two parts of this problem into separate pieces, right? The step one with the old roots, and now step two with the new roots. So I can pretty much assume that whatever the new roots are going to be the ones that create the particular solution, y sub p of x right here, that we're about to write down. So let's think about what that would look like. Y sub p of x. This would normally just be, corresponding to this root of 3, we would normally write down, e to the 3x. There would be a constant in front of it, just like we have constants in front of the terms in the complementary function. And you might think to use something like a C3 right here, because we wouldn't want to use the same constants again. So we would need a new notation. But I am actually not even going to use C3. I am going to use a different type of notation here, and I'll explain why in just a second. But I'm going to call this capital A. The reason that I'm doing that is because unlike C1 and C2, which are just general constants that will be part of my final answer to this problem, the value of A actually has a specific number. It actually can be solved for, even without any initial conditions. We can actually solve for A. Let me show you why. You see, if this is my particular solution, I should be able to plug it back into my differential equation and it should work. So let's do it. Let's take two derivatives of it right now. Okay, I'm going to take two derivatives of this particular solution. So each time I do that, I pull down a factor of 3. So by the time I get to the second derivative of my particular solution, I would have 9a times e to the 3x. And I can now plug into the original differential equation and just see what comes out of that. What's the original differential equation here? Two derivatives of y minus y. So the second derivative was 9a e to the 3x minus the original y, which was a e to the 3x. Okay, and on the right-hand side, this is supposed to be 16 e to the 3x. I bet you can solve that for a. The e to the 3x's cancel everywhere. And now I have 9a minus a, which is just simply 8a equals 16. And so it is absolutely true that a has a specific value, namely a is equal to 2. And this means that my particular solution can be specifically written down. So I have the a here, but I can be more specific because it's actually equal to 2 times e to the 3x. And that is step 2. That is my particular solution to my problem. All right, and then last but not least, we have to write down step 3. And for step 3, I think I'm just going to come right here and give myself just enough room to write step 3. But as you can recall from step 3 here, all we're really going to be doing is adding together the two boxed equations there. And if you will box them, then I am okay if people want to just write this expression into their solution and call it the final answer. This is perfectly okay to just write that. Okay, but in case you want to just kind of see how it would look and feel, we can certainly write it out in full. It'd be something like this. Okay, so there we've plugged in everything that we know to get the final general solution to this differential equation. So that first example was relatively straightforward. We had no repeated roots, we had no complex numbers, nothing like that. I want to do a couple more examples to just show you how we can work on these problems if they're a little bit more involved. And I am going to go a little bit faster through the sort of the easy pieces of this because we've already had quite a bit of practice on it. If I look at this problem right here, let's read it together. Y double prime minus y prime minus 2y equals 10 times the sine of x. I can, of course, start off by writing down the d notation for this problem, and we would have d squared minus d minus 2 of y equals 10 times the sine of x. And I can get right into this. I'm going to go fairly quickly through step one. The auxiliary equation, of course, is the first thing I would write down. We change all of the d's to r's. We factor this pretty easily. It's r minus 2 times r plus 1. Again, if we don't see how to factor it immediately, we can always use the quadratic formula on something like that to get the roots. But here we immediately obtain the roots of 2 and negative 1. So I can write down the complementary function immediately. It's c1 e to the 2x plus c2 e to the negative x. And that is step one. These roots that we've already found are what I will be continuing to refer to as the old roots. They are the roots from the original derivative operator on the left-hand side of my problem. Okay, in looking at step two, I have to think about the annihilator of 10 times the sine of x. The 10 does not matter, it's just a constant, as you'll remember. And for the derivative of sine of x, we have the annihilator, either we remember it or we look it up in our table of annihilators. It's just d squared plus 1. Okay, now I'm going to go faster through this next little piece, okay, than I did on the earlier example. I'm not actually going to write down what would happen if I apply this annihilator operator to both sides. I already know that it'll make the right-hand side become 0. And on the left side, it's just going to pile on additional roots to this derivative operator on the left side, this auxiliary equation. And it's going to give us some new roots. And actually, I only care about the new roots for step two, because the old roots were helping us to get the complementary function in step one. The new roots are always associated with the annihilator here. And of course, if I solve r squared plus 1 equals 0, I get that the new roots are plus and minus I, right? Plus and minus I. So what is the form of my particular solution then? Well, remember when we have these imaginary roots, we end up with sines and cosines as the general form of our terms of our solution. In particular, we would have, well, normally I would maybe call this C3 times cosine of x plus C4 times sine of x. Again, where am I getting this, the cosine and the sine from? Just remember, whenever you have roots of the form a plus or minus bx, right? You derive solutions that have the form e to the ax cosine of bx and e to the ax sine of bx. That's just always a fact of life, right? Complex conjugate roots of the form a plus or minus bi always are associated with solutions of this nature. And in the case we're looking at right now, the a value is 0 and the b value is 1, right? And if a is 0 and b is 1, we just get cosine and sine right here. All right, but remember that I don't want to call these constants C3 and C4. Instead, I'm going to remember that essentially these are constants that we can actually solve for. I can actually come up with values for A and B here. So I'm using two different constants this time, but that's no problem. The next step is going to be to plug this form for the particular solution into the left side of my differential equation so that I can match it up with the right-hand side. So that means I need to take a couple of derivatives of this. You can see this is a second order equation. So I would need to take a couple of derivatives here. The first derivative would be negative a sine of x plus b cosine of x. All right. And then if I take yet another derivative, the second derivative, I would have had a negative a cosine of x minus b sine of x. Okay. So those are just two derivatives of my particular solution. And now I'm going to plug them in on the left side of my problem here. Get this out of my way so I have enough room here to work on this. Just kind of come right here. So I'm just going to plug in right here. Okay, whoops. So the second derivative, let's see, what do we have? We have negative a cosine of x minus b sine of x. That's two derivatives of y. And then we have to subtract from that one derivative of y, which is negative a sine of x plus b cosine of x. And then I have to subtract 2 times the original y sub p of x, which is a cosine of x plus b sine of x. So all of that, that is y double prime minus minus y prime minus 2y. That's the left-hand side of the differential equation with this particular solution plugged into it. And I have to set all of that equal to the right-hand side, which is 10 sine of x. Before I do that, I'm going to clean up this expression here on the left side just a little bit. You see, I have cosines in several places in this expression. Let's just gather together all of the cosine parts. I have a negative a here, and then I have a minus sign on a b here. And then over here I have minus 2a. So all of that is with cosine of x. This is just algebra. This is just grouping the terms together, right? And what about the sine terms? Well, I have negative b times the sine of x, and then I have a double negative on the sine of x right here with an a in front of it. And then I have minus 2b as well, and that is times sine of x. And all of this is supposed to be set equal to what's on the right-hand side, which is 10 times the sine of x. And so now what we're going to do is match up the left sides with the right sides. So the sine of x coefficient here should be equal to 10. What is this anyway? This is a minus 3b. That's supposed to be equal to 10. The sine part has to match up on the left and the right with its corresponding term. And actually, we should match up the cosine terms as well. It's just that there's no cosine appearing at all on the right-hand side. So there's 0 cosines over there. But on the left side, I have negative 3a minus b. So the cosine coefficient here, right? That's just negative 3a minus b. And that should actually be 0. Okay? Well, from this, you actually have sort of 2 equations and 2 unknowns. And I will leave it to you to actually solve for a and b. It's not a hard thing to do. You can always use a matrix to do it. But this one is actually pretty easy to work out. A turns out to be 1, and b turns out to be negative 3. Okay? And what that tells me then is that when I come back down here to my particular solution that I had just figured out, I could plug in fact, let's just write it as a new line right here. The particular solution would be a times the cosine of x, which is just cosine of x, and then plus b times the sine of x, that would be minus 3 times the sine of x. I'm going to put a box around that as well. That's my particular solution. Okay. Feel free to pause the video if you need to soak it all in for a minute. Make sure you're understanding what's going on here. But in the meantime, I'm going to go on to step 3, which I know is easy. Step 3 is where we basically just add together the complementary function and the particular solution. So I'll write it out, but just so you can see it written out longhand. But feel free to just put this box down for your step 3. But I'm going to write it out because I just kind of like to look at it and see kind of what I have for an answer here. This is going to be it. The y of x is equal to the complementary function plus the particular solution. Now, if I had been given initial conditions, let's say they told us what y of 0 is, maybe what y prime of 0 is. If they give us those initial conditions, we can actually solve also for the C1 and the C2, but we would only do that at the very end, right where we are right now. Okay, so we wouldn't be trying to solve for C1 and C2 in the midst of doing step 1 or step 2. This would have to come at the very end, and only could we do it if we had initial values. So here we don't have any initial values, so our final answer is just the general solution that you see right here. All right, I am going to do one more example because there's still a little bit more stuff to share with you that the first 2 examples didn't show. But again, this one is going to be even faster than the first 2. Okay, it's actually a harder problem to solve, but as it turns out, we're going to take a nice shortcut. When you write down this question on your paper there, leave a little bit of room, maybe 1 line's worth of space below this question, because I'm going to come back and put some words in here. We're going to change the instructions a little bit for this particular problem, but I don't want to do that until we get to a point where it seems like we might want to do this. Okay, so let's try and solve the one that I have right here. D squared minus 4d plus 5 of y equals 8x e to the 2x cosine of x minus 3x cubed. Okay, so as usual, I already have the annihilator, or sorry, the D notation written down, so I can go straight to step 1. The D notation is here. The auxiliary equation will just be r squared minus 4r plus 5 equals 0. This one, it may look like it's going to factor nicely. It actually doesn't. This one does not have a nice factorization, but I'm not going to get nervous about that because I know that I can use the quadratic formula, right? So the roots would be 4 plus or minus the square root of 4 squared, which is 16, minus 4 times 5, and then all over 2. And if we simplify that, we're going to get 4 over 2 plus or minus the square root of negative 4, which is really 2i. But we're dividing 2i by 2, so we just get 2 plus or minus I. And so once again here, we have a pair of imaginary roots. And so we're expecting to see sines and cosines in our answer. This is the complementary function. We can straight away write it down now, right? It's just going to be C1 e to the 2x cosine of x, right? And then C2 e to the 2x sine of x. This is again coming from the older material, and we are using, again, what I like to call the old roots to create the complementary function as such. Okay, so this is not using the annihilators at all. This is just the old material for a homogeneous nth order linear differential equation, how we write down the general solution. Okay, so the next thing I need to do is move on to step 2. And in step 2, I need to think about the annihilator of the function that's on the right-hand side. And I see that there is a subtraction here. So I actually have 2 parts to the capital F of x this time. The 8 and the 3, those coefficients, they don't matter at all in deciding what our annihilator is, but we have to look carefully at the expressions that we have, and we're probably going to use the annihilator table this time, right? To annihilate x e to the 2x cosine of x, we're actually going to use item number 8, in the table of annihilators that I showed you earlier. And what we will end up with then is d squared minus 4d plus 5, and this will be quantity squared. That's the annihilator of the first term, only the first term on the right-hand side. We also have to annihilate 3x cubed. The coefficient in front, the 3, doesn't matter, but if I wanted to annihilate x cubed, I would do it using 4 derivatives, right? D to the 4th. And I have to take that annihilator and multiply it. Remember from earlier, I have to multiply that annihilator with the original annihilator. Okay. So we have these two annihilators being multiplied together this time. Now, this is going to be the source of our new roots. Okay. Of course, to get them, we would technically change the d's to r's. So our roots will ultimately be r values, but I'm just going to go right away and write down what they would be. Notice that this quadratic expression is actually the same as the one that we had on the left-hand side of the original differential equation. So the roots are just going to be, again, 2 plus or minus I, and I notice these are the new roots, by the way. These are the new roots. These are the ones that will correspond to our particular solution. 2 plus or minus I is going to show up twice because it is squared here. This quadratic expression is being squared. And then d to the 4th, which is really r to the 4th, would just give me the roots 0, 0, 0, and 0. Okay? And so, well, we have quite a handful of new roots here. Let's write down the form of the particular solution. Let's try to write down the form of it now on the basis of those roots. So I'm going to be using A, B, C, D, several different letters as coefficients here, all of which have values that we, in theory, can find. But let's be careful. The 2 plus or minus I, even though I'm calling it here a new root, it's actually repeated, isn't it? We saw 2 plus or minus I earlier when we were doing step 1. And because that root is being repeated already right here, we actually have to start that x stacking business that we normally implement whenever we have repeated roots to the auxiliary equation. So here I have a repeat. So I'm going to use capital A as my coefficient. And then instead of just writing e to the 2x cosine of x, I'm going to write x e to the 2x cosine of x. All right? That x is stacked there because this root, 2 plus or minus I, is already repeated from a root that I saw in step 1. Okay, so we have to keep track of repeats that even transcend the different steps of the process. That's kind of the thing I wanted to show you with this example. The other root, of course, would be b times x times e to the 2x times the sine of x. All right. Next, we have that same pair of roots for a third time. 2 plus or minus I again for a third time. So I'm going to keep stacking x's. C x squared e to the 2x cosine of x. And then another term, which would be, I'm going to go ahead and use d as a coefficient here. I realize that we use d pretty heavily to represent our derivative operator. And if you wanted to skip over d because that was confusing for you, that's certainly okay with me. I think I can handle it. I'm just going to leave the d there. X squared e to the 2x sine of x. And that becomes another two terms corresponding to another repeat of the 2 plus or minus I. Finally, we have several more terms that are associated with these zeros. Let's see if we can write them down. Of course, this is the first time we've seen 0, so it would just simply give us some constant times e to the 0. Well, that's just e. But then the next time we have the 0, we have to stack an x, so I'll call it fx, and then gx squared, and then hx cubed. Wow, that took a while to write this down. Okay. Now, what I want to say here, guys, is that to actually solve for the coefficients a through h would be a massive job. I would put it borderline impossible to do by hand. And so we're actually not going to do that. If we get a problem that's this messy, we're probably not going to want to actually solve for the, think about it, you would have to take two derivatives of this. All right, and even taking one derivative of this looks pretty bad because you're going to have massive product rule calculations here. It's going to be very, very messy to sort of work out a through h. So sometimes on these problems, you will see instructions, and this is why I asked you to leave a line blank up here, which is that I'm going to give you instructions that say it is acceptable to find the form of the particular solution y sub p of x. Some variation of those instructions should tip you off that you're not expected to solve for the constants. Okay, maybe it would say something like, it is not necessary to solve for the constants that arise in your particular solution. Something along those lines. Be sure to read these instructions carefully, because if you actually do start spending the time to solve for all of those constants, good luck. It's going to take a long time. So we're going to just be content with step 2 like this. It would take probably a computer a little bit of heavy thinking to solve for those 8 constants. We're certainly not going to do it on pencil and paper. Okay, so that means we can go to step 3. And now this time on step 3, of course, the final answer is just the complementary function y sub c of x plus the particular solution y sub p of x. And I do not want to rewrite this all out again because it's so long. And you might feel that way sometimes as well. And that's why I have made this comment a few times today, that if you just want to kind of write step 3 down with this thing in a box, I'm okay with that. There's no reason to make you write all of these things down again, but it is helpful if you could please box your complementary function and your particular solution, at least the form of the particular solution, so that we can easily find the pieces that would be put into these 2 terms on the right-hand side if we really wanted to write it all out. Okay, but I would consider this to be more than good enough to get the purpose of what this type of a problem would be going for. Another situation where you probably wouldn't be asked to solve for the constants is if the order of this differential equation was higher. You notice all of the examples I did today were only second order equations, but we can use this annihilator method for much higher order differential equations as well. And in those cases, taking derivatives of your particular solution here just to solve for those constants could be really, really tedious. So we're probably not going to do that. At any rate, I've shown you a few examples of how this works. Remember, the table of annihilators is absolutely essential to being able to figure out step 2 of our process. Step 1 is just a review of things we've done before, and step 3 is just writing down the final answer into a box. I hope that this has made sense. I welcome questions if you have any. Certainly take some time to practice this on your own. This annihilator method is a really, really powerful and popular method for solving nth order linear differential equations when the right-hand side function f of x is not just 0. So if we have a function f of x here that we know how to annihilate, okay, we have to have an annihilator for that capital F of x in order to apply this method. But as long as we do, this annihilator method is a very, very effective way of getting the general solution to our differential equation. Thanks so much for taking the time to watch the video today, folks. I hope you enjoyed it, and I look forward to seeing you guys again soon in another video.